they were controlled.
So they were controlled.
So taking that population, which is already very small, people who aren't.
Yeah, right. Yeah. I'm out of that, right?
Okay, and then saying, hey, you want to go sit in a room for an hour full of smoke?
That was my question.
The population of how many people are going to get to just go for it?
Sister.
16 people.
Sister.
What?
Hang on, time out. I love the question. I love the response. Don't get hung up on that. We're doing nuts and bolts today. You guys are getting very, 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 very good details. Is the nut or the bolt constructed correctly? Nuts and bolts, the test, assume the data going in is fine. I love what you're saying. Please, never think that I don't love what you're saying. But you're getting at the actual methodology of the methodology, the drawing of the sample. This is just focusing on the methodology of the test itself. So assume the data is okay for purposes of argument. I'm not saying it always is. Please hear that too. But realize that you guys are uber analyzing, which I love. But I'm not trying to get at that because we can never answer that question, unfortunately, because we don't see how they collected their data. Is that fair?
Yeah,
I'm not trying to push it off. I'm not trying to push it off. Okay, it's a great
I was
question.
just trying to address the fact
Good for you.
being upset about 16 people.
Fantastic, fantastic. That's okay. That's because it's hard to do it. All right, now friends, we've answered some of these questions already. So the first, you've got a null hypothesis, and we've got a research hypothesis, and we've already defined them, yes? Our null hypothesis is that
Has no lowering effect on
secondhand smoke does not lower lung function. No lowering effect. Research hypothesis
is that it does.
is that it does. Is that it does. That's going to carry for both 0 to 1 hour and also for 3 hours. Here is the results written into a probability statement. Chance that we got our lowered lung function data, which we did. We got data that showed lowering of lung function. What were we assuming? That it was, when we went into the study, we were assuming that secondhand smoke was not going to lower it, right? That was the null hypothesis, right? You have to strip away what you think you know about secondhand smoke, which we've been told for years and years it's bad for you. But when you go into the study, we built the curve around the fact that we knew what the average lung function without secondhand smoke was, and assuming that it was the same. So we assumed that there was no lowering effect. But then we got our data back, and the data showed a lowering effect. What do we call that again? This is going to be the universal sign for the next 5 weeks of a... Starts with a C. Boom. It's a contradiction. We were expecting no lowering, we got lowering. Contradiction. Mathematically, what does the contradiction look like? That. A very, very small probability. Think of this as probability of agreement of the two pieces. There's very, very small likelihood that there is agreement of our belief and the data we collected. Okay? Does that make sense? Think of it as a measure of agreement between the belief we went in with and the data we came out with. The less they agree, the smaller that number gets. So, does it appear that secondhand smoke affects lung function? Based on this, assuming we did it right, yes, it sure does. Could we be wrong? How could we be wrong in this case? Go, Renee. Oh, it could just be an outlier. Skylar, please. We could have just caught an outlier on the null curve. Maybe secondhand smoke doesn't have any effect, and we just so happen to draw the 5 black cards in a row on the fair deck to put us down there. It's possible. It's possible. Definitely is possible, yes?
It was fair?
Was that? You'll never know. But you can measure the likelihood of it, assuming it was fair, yes? Assuming it was fair. Renee, go.
But the more cards you drew, the more likely.
Thank you. Very good point. The more cards you draw, the more unlikely it becomes. But we only have 16 cards that we drew in this one. 16 Greek cards. So we're stuck with that. We can't go any further. Does that make sense? That's why replication is so important. Go get more cards and see if the results hold up. But based on this particular study, we could be wrong. Yes, we could. I want to analyze this and answer one of your questions from break, Renee. I want to come back to that. Here's the end result. After a baseline, the null and research, we already answered that. They're the same null and research. So here it is written as a conditional probability. Once we let them sit for 2 hours outside the smoke-filled tomb, what happens to their lung function? It comes back up. It readjusts to what we call baseline. Good. What curve are we back on, apparently? The null curve. How can we tell? That picture, those pictures back there, weren't on your little notes, right? So what tells you up there that you're back to baseline? That. right there tells you you're back. It tells you you're above 5%, which means you're no longer an outlier based on that curve. You're back on the curve. So, does it appear? Does secondhand smoke appear to affect lung function after 3 hours? No, doesn't appear to, does it? Because now we're agreeing with H0. We were agreeing with H1 after 1 hour going, oh yeah, we're down, we can't breathe anymore. But after 3 hours, it appears that it's reverted. Now, I'm not saying, Michael, there's not some long-term damage that you mentioned before. But based on what we're measuring right now, the short-term effect seems to have worn off after 3 hours. Could we be wrong?
Yeah, of course.
Of course we could. Back to this curve. Brendan, if you would. Of course we could be wrong. Think about it. Oops. Remember this curve right here? This research curve? Remember when we drew this orange guy? We drew this orange guy. And he's pretty much on this null curve. What would the orange guy be on this curve?
An outlier.
So is it possible that our orange data point, it could still be an outlier on the research curve? Of course. Now the problem is we can't measure that. And here's why. In order to measure how unlikely this is, what would you have to know?
The mean of the research.
Yes, and we don't know exactly where that is, do we? I put it roughly here, but we don't know exactly where it is, so you can't give me an exact calculation for what this is without a certain set of assumptions. That's why we're not going to attack it right now. Couple weeks, we're ready for it. But this could be an outlier on this curve, as much as it's not an outlier on this curve. Which means, to answer the question, Michael, you have a point, go ahead back there.
Well, I was just going to say, shouldn't there technically be 4 bell curves since...
Hold that thought, yes. 2 bell curves broken into 4 pieces. Can you hold that thought for me? I love that point, thank you, sir. Jerry said, thank you, Brendan. Shouldn't there technically be, it's so cool watching the camera adjust to that. Shouldn't there be 4 bell curves? We can do with 2 if we break them into 4 pieces. And if you hold that thought, which I love, give me till Monday, maybe Wednesday next week, I want to get into that. Because I want to start talking about this other kind of error. But this is the other kind of error. Could we be wrong? Yes. Our conclusion is that after 3 hours, lung function's back to normal. It might not be. Maybe it's still lowered and we caught an outlier. Does that make sense? You can always catch an outlier. Your job is to make it as unlikely as possible. Fair enough? More on that to come. More on that to come. Now, here is a great big old fat synopsis of what I like to call errors. Because you could always be wrong with your test. You could always be wrong with your test. So, here's an if. You do your study. You get a small p-value. We're going to start generating our own p-values on Monday. I promise you that. Own p-values on Monday. Suppose you get a small p-value. What does that mean? Well, it means one of 2 things.
It's out of the norm.
It's out of the norm. I love that. It's out of the norm. It's either outliers out of the norm or it's out of the norm somewhere else. And if you think about it, they're kind of saying the same thing. Good. So, you say something has changed. Something has changed. What's the chance that you're wrong?
5%.
That's the number we tend to use in the journals over and over again is 5%. When you take research methods classes, and I'm going to keep hinting at it here, sometimes you want to make that smaller or bigger based on other numbers, but we'll get into that in time. Right now, 5%. That's the kicker. Renee, you asked me about a beautiful little Greek letter. Alpha. You saw it in the research article. There he is right there. The lowercase letter a in Greek represents that. It's called the chance of a type 1 error, which means you actually got your outlier on the null curve, but you're saying it's actually different when it's actually just a flukish little random hiccup in the actual data set. That's always possible. We've assigned it a value of 5%. That's why you always see p-values either less than or greater than 5% in the journals. Sometimes you see ones like that one where it's less than 0.0001. That's still less than 5%, yes? It's way less than 5%.
But are they not using it to show that it is outlandishly
Yes, when you get an outlandishly small p-value, a lot of times they like to put, sometimes you'll see p approximately equals 0, because it's so damn small that it's almost immeasurable. Your TI will come back with p-values of 0 sometimes, you'll see soon some of those. Just because you're so many standard deviations away from average that you're essentially, you shouldn't have happened on that curve. It's all about position on the null curve. When you get a small p-value, which is less than 5%, that means there's a less than 5% chance you should have been on that null curve. Which means there's a pretty good chance you should have been somewhere else. Somewhere else. Good. Good. So that's what I call a false positive. Saying something changed when in fact, it did not. This is like taking a test. We analyzed this in 243. Here's your Lyme disease test. Positive. Then you analyze the test and you realize it's like a coin flip. If you actually have the disease, the test will catch it half the time. Oh, thank you. Here's a quarter. Save yourself some money. Essentially. So a false positive can happen. You can say, boom, it's crying wolf, if you will. Crying wolf. Something changed, something changed. You might be wrong. Maybe nothing changed. These are the ones that get overturned. These are the ones that get overturned. Because Kate, remember what you said before? Write the result, put it out there. Don't say you've proven anything. Just put your results out there. Maybe it gets disproven the next year by 2 other independent groups. Then it looks like you made a type 1 error. And you put your hands up and you go, it happens because it's probability. Fair? Fair. Good-ish? We live with that? Okay, good. Now, here was the small p-value from the article. P less than 5%. There's your alpha level. There's your alpha 5%. Our p-value came in under that 5%. Which means the article is claiming lung function parameters were significantly reduced. Were significantly reduced. Could they be wrong? Yes, maybe they're not. So what would the type 1 error be? Saying that
Lung functions reduced.
lung functions were reduced when?
If they weren't.
When they weren't. That's it. That's what a type 1 error would be. You're making the claim that you have significant reduction in lung function when actually there is no significant reduction in lung function. What's the chance of that happening? What's the chance you screw up? 5%. 5%. Assuming that lung function is actually the same as it was, you've got a 5% chance of catching it wrong and saying that it actually went down when it didn't. Is that fair? Is that fair? Ask me questions right now if you've got them. You always see alphas in research articles. You're always going to see alphas, and alpha compares directly to p-values. The one that you don't see often, and you're about to see why, is what happens when you get a large p-value. Could you be wrong with a large p-value? Of course, you can always be wrong. Of course you can. But when you get large p-values, what are you generally not? Let me ask this question the right way. Are you going to read about large p-values often? No. How come, Skylar?
Because there's
That's okay. What does a large p-value mean?
What's common?
there's no change.
There's no change. What's common is still holding. What is the null belief? Secondhand smoke. We think secondhand smoke is actually damaging lung function. Oh crap, we just put 2,400 Greek people in a room filled with smoke, we brought them out and they ran a marathon and they all set personal records. Okay, let's scratch that off. Because that's the idea. A big p-value means nothing changed. You thought something was going to change and it didn't. So you're like, okay, maybe I was just wrong. But maybe you were wrong. Maybe your hypothesis wasn't wrong, but your data came back in error. Go, Renee. Yes.
So the p-value is directly related to the question you asked?
Always. The p-value is a measure of likelihood that you're on the null curve. So you start with that null curve. Here's lung function of no smoke. Are you off or on that curve? The p-value tells you whether you think you should be off or on. A big p-value means you belong on that curve, which means nothing changed, lung function's the same. Could you be wrong?
You can always be wrong.
You can always be wrong. Good. How can you, or what's the chance of this? Trick question. Trick question.
5%.
It's not 5% necessarily.
I said greater.
Oh, it might be greater, it might be less. Here's the problem. Here's the problem. Brandon, if you don't mind, chill that for one more second. Remember these curves from before? It's pretty easy when we have the null curve to identify where 5% is. It's pretty simple. Pretty simple to identify where 5% is because we know things about the standard normal curve. I think it's about 1.645 units down to track 95% and 5%. So we know like where that number is and we know where our stuff falls. So we're happy with that. And the reason we know where this is because we know what that is. We usually call that 0. You'll see why as we go through this course, why we usually call that 0. So that's here. If you land over here, this is why you can identify alpha at 5%, is because you know where the 5% is. The problem is, if you're trying to identify a false negative, which is what we're looking at right now, that's false positive. A false negative means you got data that landed mostly in your null curve, but it shouldn't be there. So the trick is, let me use a different color. Get rid of. Here would be the false negative probability. What's that? The question is you don't know. Because in order to know, this is 0, yes? What's
You
this?
still don't know.
That is an unknown position on the horizontal axis. So until you know what that is, you can't know what that is. You see what I'm getting at, friends? So that fluctuates. We have a name for it. We have a Greek letter name for it. Kate, ask me that question. Brandon, if you don't mind. Thank you,
So
sir.
this might relates to what you just covered up.
Yeah, go ahead.
So where you had your graphs overlapping, which
Yes!
is 5%, 5%, when you land in the smack dab middle of that, where you
Oh,
technically...
chance of that is having a 0.
Okay. Was
Don't worry about
any-
that. Don't you worry your head about that. Great question. It's not going to happen on average.
Okay, good.
Great question. Great question. Don't worry about it.
Okay.
We have an answer if it ever does happen. It never will, though. I promise you with
We're good, then no worries.
99.9994% probability. Don't worry about it. Cool?
Yep,
Great
okay.
question. You're thinking a very mathematical question. I love it. So the answer to the question is, what is the chance of being wrong in that way? Right now, you just call it beta. Which is the next one after alpha, obviously. Alpha, beta. This is called a type 2 error, which we call a false negative. In other words, from our study we just did, after 3 hours, looks like the lung function came back up to baseline. Maybe it didn't, on average. Maybe it did in our sample, but what could we have possibly gotten in our sample? Just be brave. What kind of data could we have gotten in our sample? It's possible. Starts with an O. We could have gotten outlier data again, yes? We want to make that as small as possible. So yeah, I would like this to be 5% or less. But the only way to make this 5% or less is to know where that other curve is sitting. And that's tricky right now. I slapped that other curve over by the other data point because, you know, on average you're going to be close to that, but what's close? What's close? That's a precision talk, right? Now we're talking about precision talk. How do you adjust for precision? What do you remember about precision?
You have a larger.
When you have a larger sample, you get more precision. As a matter of fact, sample size is directly tied to beta. Very often, great statistical question I'm going to have you guys analyze in this course. How large a sample should you actually have run this study on if you want to show that lung function gets dropped by, say, 25%? That's a question you can answer. Using this big idea, not this is a big idea, a small idea, we do the micromanaged math idea. But using that idea, you can actually say you need at least 268 if you want to catch at least a 25% drop. And the bigger the drop, the bigger the sample you're going to need to catch it. Unless, well, let's stop right there for now. Right now, chance of a type 2 error is beta. Leave it at that. If you remember that, today's a success. What's the chance of a type 1?
Alpha.
Alpha, which is we're going to usually use,
5%.
that's going to be 5%. How can we know alpha but not know beta?
Because we know the average of the null.
Because we're setting the average of the null at 0. Because that's the null hypothesis. That's what's already being, Michael, you said, how did you say it about 5 minutes ago? What did you call the null hypothesis? You didn't use the usual or the expected, how did you? Common, thank you. You used the word common. I love that. Use different words. Null curve is the statistical kind of, this is null curve, yes. Right. Use common language, the common curve, the status quo, the commonly observable curve. Use other language, that's totally fine. Explain it to your neighbor, right? Imagine I'm your neighbor. Sorry. Actually, don't imagine that, you probably move. But the idea is, if you understand that, you also get why you can't know what little beta means. I think there's one more slide, but we're out of time, and I think it's just a synopsis anyway. On the back of that one page, I think there's one lone slide, I think.
Yeah.
I could be wrong. So you take that home with you. So here's what I would do. Oh, this is just an explanation. So here's my suggestion for next week. You got your exam in, take a deep breath. Thank you. I can't wait to read them. I'm looking forward to it. You have a project due next week, yes? It's pretty straightforward. It sounds like a couple of you guys have already done it, which is fantastic. So easy. Love that, JC. Very short. It is very short. It's Excel based, but the Excel work is mostly done for you as just writing intervals down. Knock that out at some point. I'll post a quiz or two for next week as well on this stuff. And you might ask yourself, what stuff? What math did we do? No math. Reading. Being able to pull probabilities out of the articles, just like we were doing in the slideshow. So I've got a few. I'll put one or two of those up. Do you guys want another confidence interval quiz? Or want to just let that go for right now? Or stick with this? What do you think? Confidence interval, hypothesis test, one of each?
Yeah.
Maybe one of each?
Yeah.
Mix them up a little bit? Okay, good, good. I'll put 1 or 2 or 3, maybe 3 quizzes up to see how, if, I don't want to kill you guys either. Of course, they're optional, so do the ones you want.
Still need 6,
You still need 6? Oh, we got 6 weeks, so that's kind of good.
I need
We got 5 weeks.
We got 5.
There we go. And you're most likely gonna have 8 class quizzes too. So realize that as you have your plate. Cool? Hey! I'm good.
Well, maybe not.
The more he throws out there, the more chance I have to say, yeah.
Well, after this one,
Yeah, it's not really, it just comes down to timing. I mean, when
it really does. Such a bummer too, like.
Good. I hear that too. Beautiful, gorgeous. Oh, excellent.
I didn't have any time before then. The weekend ended up being.
Assuming these numbers are right. Yes, I saw on the back you had a 6% and a 9%. So you divided them. You got 1.5. 6%. Good. Oh, but I think I made life easy to be like calling it this. 8.9 rounds to 9%. I was trying to make life easy for you. So if you put 49% or if you put 50%, you got the idea. You know what you're not putting? 0.0%, 0.01%, 0.2%, 212%. I'm not going to get you to take about 48 versus 50 because they're essentially the same number.
Perfect, okay, cool, that's what I was.
Rest your mind, rest your mind. Rest your mind, no worries. Oh, you're welcome. Hi.
243.
Oh, yeah, come, one of you guys just, would you mind flipping the screen and just closing that? Thank you. All right, let's take a look at that, Dawn.